really happy.
Sorry, let me introduce you, Isabella. Hi. Welcome everybody to today's seminar. I'm very happy to have with us Isabella Ianni from Università di Roma La Sapienza. She's going to talk about new solutions for the planar Lane-Emden problem. Isabella, thank you very much for accepting our invitations. Please go ahead.
Thank you, Alberto. I'm really happy to give this talk in Mexico City. And okay, so I will discuss about the existence of some new unexpected solution for a planar problem. The problem is the following. It's a very easy question. It's the Lane-Emden problem. So I have a power type nonlinearity, and omega is a smooth bounded domain in the plane, so we are in dimension 2. The power is greater than 1, so it's a superlinear problem. And we have 0 boundary condition. And even if this problem looks really easy and just there is someone, but I
I
cannot.
will take care of all this.
Yeah,
Don't
you
worry,
can.
Isabella.
Thank you.
Yes.
I have push pop up every time. So there is even if it looks really easy and simple, this equation, actually the set of solution is extremely rich and depends on the value of p of the power here, and also on the domain omega, on its topology and geometry. And the characterization of the set of solution, a complete characterization, is still open, especially as we will see in a moment for sign-changing solutions. And in this talk, I will review the characterization results which are known, especially for positive solution. And then I will discuss about the existence of new solutions for this problem, sign-changing solutions for this problem. So let me start with positive solutions, which are very well studied. And first of all, for any set omega, for any power p of the nonlinearity, there is always a positive solution. And you can find it very easily by standard variational method. So you, for instance, may minimize on the Neari manifold, or you do some constraint minimization. And so you always find a solution. And then there are many multiplicity or uniqueness results depending on the set or on the power p. For instance, if you consider a domain which is a ball, for instance, the unit ball, then the solution is radial. This is because of the Gidasny-Nirenberg result. And so you can prove that it is also unique. So in the case of the ball, there is a unique positive solution, but there are many, many examples of domains for which there are more than one positive solutions, like, for instance, the dumbbell domain, this one, or domain which have some hole, some topology. And I want to quote this paper by Esposito, Musso, and Pistoia, where in these cases, so dumbbell domain are non-simply connected domain, for P large, they were able to prove the existence of a lot of positive solution. And in particular, when P becomes larger and larger, this solution behaves like in this picture. So they concentrate at a finite number of interior points, and so they are called spike solution, and they stay bounded. So when p goes to plus infinity, they go to 0 everywhere, but in some points, and at these points, the solution stays uniformly bounded in p. And oh, this is actually what happens in general. So this was an existence result, but then together with Francesca De Marchis and Filomena Pacella, we gave a complete characterization of the behavior of positive solution when p goes to plus infinity. And what we approved is exactly the following. So we consider families UP of solutions, of positive solution, under a uniform energy bound, this blue bound here. And we can prove that up to a subsequence, they concentrate at a finite number of finite of points in the interior of the domain omega. In particular, so UP goes to 0 everywhere, but in the point, and we can prove this kind of convergence. So PUP, which is blowing up, blows up like the sum of k green functions located at the points, and k is the number of points. Moreover, around each point, the solution converges to square root of e. The local maximum converges to square root of e, this magic number. And the points of concentration may be actually characterized because they are critical point of this function, which is a Kirchhoff root function. Here, g is the green function, and h is the smooth part of the green function, this one. And moreover, if we zoom around each concentration point in a proper way, which I didn't write, but okay, you zoom with a suitable parameter, what you see when you pass to the limit around each concentration point is this profile U in red, which is a radial solution of the Liouville equation in the whole R2. And it's quite understandable why you converge to a solution of the Liouville equation, because you have a solution UP of a power nonlinearity, and when p goes to plus infinity, u to the p converges in some sense to the exponential nonlinearity. So that's why, in a sense, in the limit, if we scale properly, this is what we see around each concentration point. So, moreover, this is all that can happen for positive solution because we have an energy quantization in the limit. So the total energy, which was uniformly bounded, converges to k times 8 pi e, so to a multiple of 8 pi e. K is the number of peaks of concentration points, so this means that each point brings the same amount of energy, which is exactly 8 pi e. 8 pi is the energy of this profile, and E comes from square root of E. That's why we get this number. So energy quantization means that nothing else is possible, and so this is what happens for P large for any positive solution to this problem. And this result, some partial results were already obtained for least energy solution by Lane-Emden and Adimurti and Grossi. For least energy solution, what happens is the same, only that the concentration is at exactly one point. There is only one concentration point. And in particular, if you are in the case of the ball, for which you know that the solution is unique, then by symmetry reason, this unique concentration point is the origin. So there is concentration at the origin, and all the rest is the same. Okay, so this is for positive solution. The picture is really clear, especially for P large. And so if we want to prove something new, we have to look for sign-changing solutions. And first of all, there are a lot of sign-changing solutions, much more than positive solution. The existence can be proved for any set omega, for any P, and you have at least infinitely many sign-changing solutions because the nonlinearity is odd, so you can use some Lusternik-Schneerman category argument. In particular, if you do this argument when the set omega is a ball, you find infinitely many sign-changing radial solutions. And a characterization like the one we saw for positive solution is extremely difficult because there are many, many more situations which are possible. And among sign-changing solutions, we can consider least energy sign-changing solutions. So these are the sign-changing solutions which have least energy among all the possible sign-changing solutions. And there is a paper by Barsh and Vett where they studied this kind of least energy sign-changing solution. They proved that they have exactly two nodal regions, so they can be characterized a bit more. And also they can compute their Morse index, which is always equal to 2. And moreover, if you are in the case of the ball, this least energy sign-changing solution, even if they are sign-changing, they inherit partially the symmetry of the domain. So they are not radial, but they are foliated Schwarz symmetric. What does it mean? It means that they are symmetric with respect to an axis, this axis here. Oh, sorry. And also they are strictly monotone in the polar angle with respect to the axis. And moreover, you can prove that the nodal line, this NL is the nodal line, intersect the boundary of the domain. This is something due to Attalion-Pacella and then Pacella-Vet. So in particular, they are non-radial. And moreover, for P large, when P goes to plus infinity, the asymptotic behavior of least energies and changing solution has been completely described. What happens is something really similar to the case of positive solution. So there is again concentration, but now the concentration is at 2 points, one in the positive part and one in the negative part. And you can describe the way the concentration appears. So the solution goes to zero everywhere, but in the points. At the local maxima and the local minima converge to square root of E and minus square root of E. And the total energy converges to twice 8 pi E. So each point brings the same amount of energy. And moreover, again, if you scale properly, you zoom a bit the solution around each concentration point, what you see is again the bubble profile, the profile U we had before for positive solutions. So also for this kind of least energies and changing solutions, you have two concentration points and the concentration is simple, okay? So nothing else happening. And then you may hope for something different. So for instance, if you are in a ball, you have other solutions. You can play with the symmetry a bit. And for any P, you can prove the existence of infinitely many sign-changing solutions which have some invariants, symmetry invariants. For instance, you can prove, you fix K, a natural number K, an integer number K, and you can find a solution which is invariant by rotations of angle 2 pi over K, and which is also symmetric with respect to the x-axis. How you do it? Just look, for instance, at one of these pictures. This is the case K equal 2. You consider the positive solution, the unique positive solution in this spherical sector. And then you just reflect it. It is symmetric by Gida's Nuremberg result with respect to the x1 axis. And then you just reflected it in an odd way nearby, and then you reflect it again in an odd way nearby, and say you get something which is symmetric invariant by rotation of angle 2 pi over k, and which is also symmetric with respect to the reflection with respect to the x-axis. And you can do it for any k. So that's why you get infinitely many sign-changing solutions, which are different from the least energy, different from the radial one. And how do they behave in the asymptotically when p goes to plus infinity? Where the solution again have simple concentration points. And this is because if you just look at the positive solution in the, let's say, in the spherical sector, it concentrates at 1 point because it's a least energy. And then by reflection, you have concentration on multiple interior points. So again, for this kind of solutions, you have simple concentration points similarly to what happened for positive solutions. And then there are also some papers by Esposito, Musso, and Pistoia where they were able to build solution concentrated and symmetric points similarly to these infinitely many odd symmetric solutions. So the question is this can we find a characterization for sign-changing solutions or not? Do they behave like the positive one or not? And for them, some years ago, for sign-changing solutions, we find a partial asymptotic characterization, which is the following. So we consider family UP of sign-changing solutions under a energy uniform bound. And we can prove that they concentrate at a finite number of points in the domain. So the solution goes to zero outside of the point and does not disappear And if you scale around each point, again, you see the usual profile, capital U. But the point is that, this is the usual profile. The point is that there is no energy quantization in general. And so this means that something different may happen. So the concentration may be not simple. And this was one of the main questions about sign-changing solution for the Lane-Emden problem. And the answer comes from radial solution, because if you consider radial solutions in the case of the both, so they are infinitely many, and actually, if you fix any n, any number n of nodal regions, you find exactly one radial solution which has n nodal regions, up to sign, because if u is a solution, also minus u is a solution. So let us fix the solution which is positive in the origin. So you have exactly one solution with one nodal region, exactly one solution, radial solution with two nodal region, and this was proved by Kajikiya in the 90s, this uniqueness result. And they are really nice because actually the solution with the n nodal regions, which I will denote by up rad n, is linked to the solution with n-1 nodal regions just by scaling. You cut the solution here in Rp and you scale back, and you in this way, and you get the solution with one nodal region less. So if you can study, for instance, the solution with two nodal regions, then from this you can deduce something for the solution with 3, with 4, and so on. And so using this scaling argument and a lot of many other arguments, some time ago with Alberto Saldagna, we were able to completely characterize the asymptotic behavior of the sign-changing radial solutions for this problem when the exponent p of the nonlinearity goes to plus infinity. So what we proved is the following. So first of all, so n now is fixed. So we take the radial sign-changing solution with n nodal regions. And we first proved that the energy, the total energy, converges to something. So it's bounded. So this means that the solution concentrates at points. Since it is radial, this means that the solution concentrates only at the origin. So the radial solution must concentrate, and it concentrates only at the origin. Then we could prove how the concentration appears. So PUP converts to a multiple of the green function centered at 0. These numbers in blue are just constant, known constants. And also the L-infinity norm, which is now attained at the origin, exactly at the origin, converges to some constant. So the solution is disappearing everywhere and again concentrated at the origin. And okay, these constants are actually known because they all depend by this theta. This is a sequence which is defined recursively, and we can compute every number in the sequence. So they are known. And then we try to understand how this concentration in the origin for the sign-changing nodal solution was happening. So we studied the behavior of the zeros and the critical points of the solution. So in my notation, R1, R2, R3 are the zeros, the n zeros, and S1, S2, S3 are the critical points, maxima and minima alternated. And what we have proved is that all the zeros and the critical point are going to 0. They are going to 0 exponentially when p goes to plus infinity. These are capital R and capital S are constants, known constants, strictly less than 1, so that's why this is going to 0. And also the minima and maxima value are going to some constants, which are greater than 1 and known, actually. And we know more because, as you can see, so everything is shrinking to 0, so all the radius and all the critical points are going to 0. And we know also the speed, because you see these numbers Rin and Ri plus 1n are ordered. So this means that we know that the speeds are ordered. In particular, the closer you are to the origin, the faster you go towards the origin. So the first zero is going to zero very fast, the second zero is going to zero a bit slower, and so on. The last one is the slowest one. And using all this information, okay, these constants are known, we can compute them, they depend on this sequence theta I, which I showed to you before, but this is not important for what I'm saying now. But what we were able also to prove using this very sharp information is that the concentration point, which is the origin, is actually a non-simple concentration point and isolated for the solution. What does it mean? It means that the solution has a tower of n bubbles near the origin. In particular, we can define this scaling parameter epsilon IP, depending on the speeds which are going to zero. And we scale our solution, radial solution U rad n in this way. So U tilde is just a rescaled version of my solutions. So I'm just zooming around the origin. And what I see is the following. So the scaling parameter are going to zero. The first scaling profile, so if I scale with the smaller parameter, let's say, converges again to U, capital U, which is the usual bubble, so the usual profile solution of the Liouville equation in R2. But if I scale with different speeds, what I see is a different profile. So in particular, all the other scaling converges to this profile capital Wi, and this Wi is this function here. This is a radial solution of the singular Liouville equation in R2. So there is, oh, disappeared. There is this term appearing here, and this theta I are the same constants which the building block of our solutions, the one I showed to you before. And this singular Liouville equation admits a radial solution. The classification is due to Prajapati and Tarantello. And so this is the profile that we see if we zoom with a proper speed around the origin. So I want to stress that this epsilon, the scaling parameter, are the first one is a small law of the next one. So these different profiles are appearing one after the other at different scale. So the first one appearing is the capital U, then we have W1, then we have W2 at a smaller scale, one after the other. So another way of saying this, which is maybe more clear, is the following. So our nodal solution with n nodal regions, when the limit, when p is going to plus infinity, behaves like the superposition of n different profiles and bubbles. The first one, up tilde, is a rescaled version of u blowing up in the origin, and the next one are rescaled version of this W1, W2, W3 with alternating sign. So they appear one after the other, and so that this is called a tower of bubble of n different bubbles. And so this means that zero, the origin, where everything is concentrating, is a non-simple isolated concentration point. Previous results were known in the case of two nodal regions by Grossi-Grumont Pacella. And also in the case of two nodal regions, with Francesca De Marchis and Filomena Pacella, we were able to prove the existence of solution having a tower of two bubbles for more general symmetric domains, not only in the case of the ball. And very recently, Pistoia and Ricciardi proved the existence of solutions for P large with a tower of n bubbles, which are exactly the same profiles that we have in the radial case, but in general symmetric domains. So this behavior seems to be really something really which can happen in more general domain, not only for radial solution. So just summing up what I've said up to now, in the case of the ball for P large, so this is the problem I'm considering, I'm looking at sign changing solution, and on one side we have seen the existence of a lot of solutions, sign changing solution, which concentrate at a finite number of points, and the concentration is simple and isolated. So when we scale around each point, we see the standard bubble. This is the case of least energy and for odd invariant symmetric solutions, also the Esposito-Musso-Pistoia solution. And then on the other side, we have the case of radial solutions, sign-changing radial solution, which concentrate at the origin, and the concentration is non-simple because there is a tower of n bubbles with different profiles appearing in the limit as p goes to plus infinity. And so the obvious questions are, can we find other solutions, for instance, in the ball? And in particular, is it possible to have non-simple concentration points besides towers? So something different from tower. And this is what my talk is about. So we will discuss the existence of new solutions in the case of the ball, and also the existence of new concentration phenomena, non-simple concentration phenomenon for this problem. So in order to catch new solutions, let me define VPK to be a sign-changing solution which has least energy among all the k-symmetric solutions. So it is k-symmetric and it has least energy among all the sign-changing k-symmetric solutions. What do I mean by k-symmetric? I mean a solution which is invariant by rotation of angle 2 pi over k with respect to the origin and reflection with respect to the x-axis. So when k is equal to 1, so no rotation invariance, this VPK, the least energy, is actually the real least energy, so nothing new. But when k is different from 1, so greater or equal than 2, so when we have some rotation invariance, this is not the least energy. And so it could be something with a lot of symmetry. So this is the case k equal 4. So it could be the odd symmetric solution that we saw before, which are already known, or maybe something like this, or like this. It could be even radial, no? But actually, this is all these situations. So this is all just a picture of functions which are invariant by rotation of angle 2 pi over 4 and by the symmetry reflection with respect to the x-axis. But actually, since I'm considering least energy, so my solution must have some least energy property, I have an energy bound for this VPK because their total energy would be less or equal than the total energy of the radial sign-changing solution with two nodal region, this one. And this, I know the energy of the radial. This is the characterization, the sharp characterization we did before. So this was this blue number, which can be computed because θ1 we know. And this number is something which is strictly less than 5 times 8 pi e for P large. And this means something because following some proof by Ren and Wei, adapting some proof by Ren and Wei, we can prove actually that for P large, if you have a nodal region, this nodal region must bring an amount of energy which is at least 8 pi e. So this means that if you have this bound, your least energy symmetric solution cannot have more than 4 nodal regions. So this situation, for instance, is not possible. This is not possible as well because you have 5 nodal regions. This is not possible as well. And so actually, if you have enough symmetry, you can delete a lot of cases. And what we proved with Francesca and Filomena was if your symmetry is at least 4, then for P large, your solution is such that the nodal line does not pass through the origin, so you cannot have this situation because otherwise you have too many nodal regions. Moreover, the nodal line does not intersect the boundary, so you cannot have, for instance, this or this situation because the nodal line, the nodal regions are too much, they are more than 4. In particular, we can also have an estimate of the Morse index. M is the Morse index for me. We can prove that each nodal region is k-symmetric, so it is invariant by these rotations and reflections. And so at the end, there must be only 2. So what remains are the 2 following situations. Either the solution is radial, so nothing new, or it is not radial, but it is like in this picture. So the nodal line, it has 2 nodal regions. The nodal line goes around the origin and does not touch the origin and does not touch the boundary. And moreover, it is k-symmetric. And of course, if this is the question is this VPK, the least energy symmetric solution, is it radial or not? Because if it is not, then it is new. This one would be a new kind of solution, quite unexpected in the case of the ball. And with the Francesca Gladiali, we were able to show the following. So the following theorem, which is summarized by this picture. So in the horizontal line, you have the power P. On the vertical line, you have the symmetry K. And orange means non-radial, and blue means radial. So we have proved that the least energy symmetric solution is non-radial in quite a number of cases. So when k is equal to 1, we already knew it was not radial because it was the least energy. But when k is equal to 2, so we have a bit of symmetry, it is not radial both when p is close to 1 and for p large. If we have higher symmetry, we can prove that it is radial when p is close to 1, but then for p larger, it is non-radial. And so in particular, if the symmetry is more than 4, greater or equal than 4, because of the previous result, we can prove that the solution is like this when symmetry is 4, or like this when symmetry is 5. So it's non-radial, but it is k-symmetric. And in both these 2 cases, we have found 2 new solutions, unexpected new solutions in the case of the ball. For higher symmetry, we know that the solution is, let's say, quasi-radial, but maybe it could be radial. So this is not clear, and we do not have result in this case. How can we show that the solution is non-radial? That this least energy symmetric solution is different from the radial one? So just to give you an idea, so I have this least energy symmetric solution, and I want to prove that it does not coincide with the radial one, so with the solution with 2 nodal region and radial. The way we did it is to compute their Morse indexes and show that they were different. So M for me is the Morse index. For the radial solution, for P large, the computation of the Morse index is doable using the asymptotic sharp characterization that we got with Alberto. So in particular, the radial solution with n nodal regions has a Morse index, which is this number. So it depends only on the number of nodal regions for P large. And this number is nothing else than the sum of the Morse indexes of the bubbles, the profiles, which are in the tower of bubbles. So this radial solution has a tower of bubbles, and each bubbles, it's known. We can compute their Morse index. If we sum all these Morse indexes, we got the Morse index of the radial solution for P large. And we can compute also the Morse index of the radial solution when P is close to 1. And we have this number. Again, it depends only on the number of nodal regions. And here the proof is again done by asymptotic analysis, because actually when p goes to 1, the power in the nonlinearity, the solution converges to eigenfunctions of the Laplacian. So the nonlinear problem goes to a linear problem, so the solution go to eigenfunction of the Laplacian. They are radial, so they go to radial eigenfunction of the Laplacian. And the Morse index of the radial eigenfunctions of the Laplacian in the ball are known. So this is how we compute the Morse index of the radial solution when p is close enough to 1. Anyway, summarizing, we can compute the Morse index of radial solution for p large and for p close to 1. And in particular, in the case of the radial solution with two nodal regions, we have these two numbers, 12 for p large and 6 for p close to 1. So for radial solution, we are fine. But if we want to compare the Morse index of radial solutions with the Morse index of this k-symmetric invariant solution, we need to compute also this other Morse index. And this is not easy, because the invariant k-symmetric least energy solution is really much more difficult to describe asymptotically, both in the limit as p goes to plus infinity and in the limit as p goes to 1. But since they are least energy, instead of computing the total Morse index, we can compute the symmetrical Morse index. This mk now is the symmetric Morse index, and they are least energy, so their symmetric Morse index is 2. So now the question is, can we compute the symmetric Morse index of the radial solution and compare these two numbers instead? And yes, we can, because during a spectral decomposition, we could actually identify the symmetries of the eigenfunctions. And so we were able to compute the Morse index, the symmetric Morse index of the radial solution. And this Morse index is these numbers, is given by these numbers here. So these 4, 3, 7, these are the k-symmetric Morse index of the radial solutions when we can compute them. So you immediately see in the orange part, which is the non-radial part, it's where you have a symmetric Morse index for the radial solution, which is not 2. So it's 4, 7, 3, and so on. So it's not 2, and it's different from 2. This means that your radial solution is different from the symmetric solution. So the symmetric solution is non-radial. Instead, here in the blue zone, you have exactly 2. So the radial solution and the symmetric solution have the same symmetric Morse index, 2. But this is not enough to say that the solution is actually radial, so we have to prove it in a different way, but I will skip this part for the moment. So this is how we could prove that in all these orange cases, the solution is non-radial, and so combined with our previous result, for when the symmetry is large enough, 4 and 5, in these two cases, we got this new symmetric sign-changing solutions in the case of the ball. And then I want to stress that in the case of symmetry 3, 4, and 5, as you may see, you have, if you take this symmetric solution, then it is radial when p is close to 1, and it becomes non-radial for p large. So this suggests that maybe a bifurcation may happen in this case. And together with Francesca Gladiali, actually, we were able to prove that this is the case. So there is a bifurcation phenomenon from the second radial solution. So we take the solution with the radial solution with two nodal regions, and we could find 3 different values of p at which there is bifurcation. So p, now the power, is my bifurcation parameter. And moreover, what we could prove is that close to the along the bifurcating solution has some symmetry. In particular, at the first bifurcation point, we have a solution which is 3 symmetric, at the second bifurcation point, a solution which is 4 symmetric, and at the third bifurcation point, a solution which is 5 symmetric. And moreover, close to the bifurcation point, since it is bifurcating from the radial one, then the nodal line does not touch the boundary and does not intersect the origin. So it really, the solution looks like the picture I did. The 4 symmetric case and the 5 symmetric case is not new because we already got this kind of solutions in the previous result. But the 3 symmetric case was something new because in the case of 3 symmetry in the previous theorem, we were not able to prove that our solution was with this shape. So we got another new solutions in the case of the ball. And why there is this bifurcation? Because as we saw before, the radial solution has 2 different Morse indexes for p close to 1 and for p large. So there must be a change in the Morse index. And when there's a change in the Morse index, this means that for some values of p, there is some degeneracy. And so that's why we got some bifurcation. But in order to separate the branches and to get actually 3 different branches with these exact symmetries, we had to work in some cones of symmetric and monotone functions, like following some ideas by Denser. So this is how we got this result. And then one could try to understand maybe if these solutions exist for any p, so if we can extend the branches, if they do coincide with the least energy symmetric solution that we find in the previous theorem, and in particular, what is the asymptotic behavior when p goes larger and larger for these new kind of solutions. And there were some numerical approximation results by Fazekas, Spacella, and Plum, where they were able to prove the existence of some approximation of solutions. So they were able to prove the bifurcation numerically, and what they obtain is exactly the same as we did theoretically. So they got this bifurcation from the second radial solutions at 3 points, and they can actually from this numerical result, we can actually see that the bifurcation appear very early in P. So the first bifurcation point is for P less than 2 even, then P less than 4, and the third bifurcation point is around 10. And the solutions that they found, bifurcating from the radial one, have exactly the same symmetry of the one that we find theoretically, but they were able, with this numerical approximation, to follow the branches in P and get some interesting result. This is the case, for instance, of 3 symmetry. So you see when P becomes larger and larger, this is for P equals 10, this bifurcating solution is like concentrating really fast in the origin, and then it seems like that it develops 3 negative peaks, and the same happens for the case of 4 symmetry. So you have a solution concentrating at the origin very, very fast, and then 4 peaks around, and the same for symmetry 5. And moreover, it really seems that when P increases, these approximations have the negative peaks, which are going closer and closer to the origin. So it seems like there is a cluster phenomenon, so a non-simple concentration in the origin, which is a cluster. What does a cluster mean? A cluster means that there is a peak at the origin very fast, and then maybe a certain amount of peaks around the origin, which are slower, and then these peaks around the origin collapse towards the origin at a different speed. And so the question now is, in the case of symmetry 3, 4, and 5, for which we do have exact solution for the problem, can we characterize the asymptotic behavior of the solutions? can we study the asymptotic behavior of this solution as p goes to plus infinity, what is happening? So, do we have clusters of bubbles like it is suggested by the numerical approximations? And I want to stress that if there is enough symmetry, at least 4 or 5, for sure there are no simple bubbles. And the reason is really simple, because you know that each bubble brings an amount of energy, which is 8 pi e, and we have a bound in the energy, an upper bound. The energy is strictly less than 5. So if you have too much symmetry, at least 4, then you cannot have too many bubbles, you know, and so you cannot have bubbles. So either you have a cluster or you have a tower. And if you put a lot of symmetry, this least energy symmetric solution should actually be radial. This is what we expect. And if they are radial, they should be towers. They are towers, because this is the characterization result of radial solution with Alberto Saldana. And moreover, we know that if the symmetry is really high, let's say at least 11, then for sure you have a bubbles of towers, a tower of bubbles. And this is even in more general symmetric domains. So the question is, can we have a cluster at least when the symmetry is 4 and 5? And the existence of clusters is the last result that we recently got. And this is a joint work with Battaglia, Luca Battaglia, and Angela Pistoia. So we fix symmetry 4 or 5, and for P large, we have proved the existence of a sign-changing solution, which is k-symmetric, and which behaves in the following way. The solution looks like the superposition of two profiles when P goes larger and larger. We are in the ball. The first profile is the usual one. So it's just a rescaled version of the standard bubble, rescaled by a parameter alpha P, which is going to 0, which is known explicitly. I didn't write it, but it's known. And so when alpha P goes to 0, this first profile is blowing up at the origin. So there is concentration this way. But the second profile is something new, because it is this profile that I called VP. And it is a non-radial solution of the singular Liouville equation in R2, where now the singularity depends on the symmetry. So this power is 2k minus 2, where k is the symmetry, which I have fixed. And this point zeta p is in the interior of the ball and different from 0. And this is scaled in beta p. Beta p is a parameter which is going to 0, so it's a scaling parameter. So this means that when beta p goes to 0, this second profile blows up at k points, which are the k roots of zeta p. So these are the k root of zeta p, and this solution picks up at these k symmetric points around the origin, which are these k roots. And moreover, if we denote by rho p the distance between each root and the origin, then also this number rho p, this distance, is going to 0 when p goes to plus infinity. So what is happening is that the solution is concentrating at the origin, concentrating at these k points, and these k points are collapsing to the origin. And moreover, we know all these speeds, alpha, beta, and rho, explicitly. They are going to 0 exponentially. And in particular, alpha is small law of beta, and beta is a small law of rho. So this means that you first see the solution concentrating at the origin with a standard bubble really, really fast. Then you see the second profile concentrating at the k roots. And then at a lower speed, you see that all these k points are collapsing toward the origin. And so this is exactly what a cluster is. So we found a cluster solution two cluster solution for symmetry 4 and symmetry 5. And some final remark. So this is the first example of solution of this Lane-Emden problem, having a non-simple and non-isolated concentration point, so a cluster point. And also the use of this profile is completely new. This result is in dimension 2. In higher dimension, the problem is completely open, even if we expect a similar behavior, maybe. We can consider more general symmetric domains than balls, but I just did it in the ball. And something about the proof. The proof is based on a Lyapunov-Schmidt finite dimensional reduction, really, really technical. So in this kind of proof, what you do is you make an ansatz, so you approximate your solution, and this is our ansatz. And then you show that for P large, the error that you are committing is really small. But actually, this ansatz is not the good one in order to take care of the error. And we had to add two lower order terms, lower order profile, both to the first bubble and to the second profile. And so you may see that the proof gets really, really involved. Anyway, we could get the result only for k equal 4 and 5. And this is the only case where our construction works, even if we expect the cluster to exist also in the case of symmetry 3. But for symmetry 3, the problem is really still open. Maybe the construction that we did should be refined more. And the same profile, the second profile, should be also working to build solution for different planar problem, like for the H-Gordon equation, or also for some exponential nonlinearity type equation. And this is something Luca Battaglia is doing now. This is a work in progress by Luca Battaglia. And finally, just few open problems, because once we have opened the door, there are this kind of solutions. So now we expect to have much more solutions. For instance, bifurcating from the solution, the radial solution with 3 nodal regions or more. And so if you bifurcate from this radial solution with 3 nodal regions, you will have something like this. And why we expect this to be possible? Because we can compute the Morse index of radial solution with 3 nodal regions, and for P large and for P close to 1, it changes. So again, you may expect to have bifurcation. But which are the symmetries in this case is still open. By our computation, in this case of 3 nodal region, this should be the symmetries that you have. And there are some numerical evidences by Fazekas, Pacella, and Plum. In the case of symmetry 5, 6, and 7, they were able to find these 3 bifurcation points. They were able to follow the branches. And so again, you have concentration. So the question is this a cluster again? And how is the solution for P large? Is it the superposition of more than 2 profiles? What is the next profile, the third profile? So these are all open questions, even for a higher number of nodal regions. And I think that I will stop here and thank you for the attention.